let's recall there's line integral of a scalar field. So a function lowercase f, maybe f of, let's just go with x comma y. There could be a comma z, but let's not worry about that. And that's different from a line integral of a vector field. And just for simplicity's sake, let's not use a three-dimensional vector field. We're just going to go with a two-dimensional vector field for now. Okay, these are different. There is a connection between these, but it's best to think of these just really differently. Now we've seen, if we're now at the end of the chapter, that there's actually many passing back and forth using some theorems you can do, but if you're going to go ahead and do this directly, what you do is you also need to be, given a curve C. So let's maybe mention that over a curve C. What you do is you parameterize the curve C. In the case of a scalar field, what you end up doing is probably just writing, your x of t equals whatever it equals and your y of t, and you have t going from A to B. And then ds is equal to root x prime of t quantity squared plus y prime of t quantity squared dt. So if you're asked to compute the integral over c of f, we'll just leave off the of x. Let's just f of x comma y, let's put it in there, ds. This would turn into the integral of t going from A to B of f of x of t, y of t. So we go ahead and replace x and y that appeared here with the appropriate expressions coming from the parameterization. And then the ds gets replaced with, well, this here, right? X prime of t, quantity squared, plus y prime of t, quantity squared, and then a dt out there. We should just also comment, as long as we're here, right? So if that's the ds one, then dx is x prime of t dt. So in the same way, if you're asked integral of f of x comma y dx, this would be the integral t going from A to B of f of x of t comma y of t, but then the dx gets replaced with x prime of t dt. And in the same way, dy should be y prime of t dt. So integral over the curve C of f of x comma y dy should be integral A to B f of x of t comma y of t y prime of t dt. Now we could, I think including this information about this, sort of morally speaking, a composition going on is helpful, but if we just were to leave it out, it would look like this, okay? And just kind of erase all of that. And then maybe we'll just kind of clean up how this looks a little bit here. Just push things over a little bit. Same deal here. I'll just move that a little bit here and do this. Now what about over here? So you'd have a vector field to start with, and this vector field, say of x comma y, and we might just leave that out. Okay, we'll include it sometimes, we'll not include it sometimes. So let's write this, and then this would be p of x comma y comma q of x comma y, and again, out of trying to not write too much all the time, we might just write capital P comma capital Q. So unlike before, where the curve C is parameterized just as standard parameterization style format, now the curve C is parameterized using a vector function, so x of t comma y of t. And again, you might be in a three-dimensional scenario, but let's just for simplicity go with two-dimensional. Then r prime of t is x prime of t y prime of t. Okay, and then the integral over the curve C of the vector field f dot dr is equal to, well, integral t, should have included here, sorry, t going from A to B. So the integral t going from A to B of f of r of t, okay, times dotted with dot product r prime of t dt. Now I'd like to actually, I think it'll help for what we're doing right now, just the things we're trying to clarify. This composition looks a little funny because there's two things here and there's two things there. So let's be real clear what we mean about this. Okay, so this f of r of t is really actually, in the end, somehow poor notation, but it's what we do. It's p of, and then x of t, y of t, comma q of x of t, comma y of t. I hope all those commas are in the right place. I thought those look right. Okay, that's what's really actually going on. Well, let's actually, based on how that's written, let's write this out in a little more detail. This is actually integral a to b. So let's do this, right? So it's going to be a little messy, but okay. And then, yeah, let's just, so it's p, it really is just p comma q dot, and then r prime of t is x prime of t, y prime of t. So I just, this really is just shorthand notation for all that. It just means that the vector field itself needs to be written in terms of t instead of in terms of x's and y's. And if you work out what this is, well, integral a to b of, this dot product, right? So p times x prime of t plus q times y prime of t dt. And if we just write this as two separate integrals, we have integral a to b of, again, that's really p written in terms of t alone, x prime of t dt, plus integral from a to b of q times y prime of t dt. So why bother writing all of this in this format? Let's go back here. We said if little f here was a scalar field. Well, capital P is a scalar field. So what we could do is actually just replace the little f's here with capital P's and replace the little f's here with capital Q's. And so the point is, based on how this and this are written, you'll note that the integral with respect to c of p dx plus q dy, this is all one thing, and it's just shorthand notation to mean these two integrals right there. Yeah, so let's actually just write it out. Integral over c of p dx plus integral over c of q dy. And then if we replace those with what's on the right side here, we'll have integral a to b p x prime of t dt plus, now copying this integral a to b q of y prime of t dt. And so you'll note that actually the same thing is written twice here. So these are really different in terms of actual implementation. However, it's this type of integral here that occurs twice, namely here and there, so that you can actually, there is a sort of connection back and forth, but not to this ds integral, right? This is really truly something just different. But when you have this integral of the scalar field with respect to coordinate axes, either with respect to x or with respect to y, and then you add one of each kind of these things with different functions here, if you'd like, p and q, then you end up with the same thing as if you're doing the line integral over a vector field.